Hi everyone. Thanks for tuning back in to Mind Over Math. This is part two of a three-part series on limits. This is on the indeterminate. Indeterminate means it is irreducible by factoring, or it is reducible by factoring. So as it turns out, here's a problem where I would know what that graph is. When I plug in my 1, substituting, I get 0 over 0. Well, that's good news and bad news. The good news is you can reduce this. The bad news is you can reduce this. So we're going to do grouping by 2's. Take the first group as x squared out. We get x minus 1. In the second group, x minus 1, we take a 1 out, and these two outside the parentheses become x squared plus 1 times the common parentheses, which is x minus 1. Now you'll notice here that we got a great thing occurring. We have x minus 1 and x minus 1, which just cancels. We just simplified this problem tremendously by factoring it. So the x minus 1 cancels. That leaves me x squared plus 1. Now I go back to the x equals 1, which gave me 0 over 0 here. And I just plug it in again for x. I go right back where I was, and I get 1 plus 1 is 2. This radical x over the square root of x plus 1 minus 1, when you plug in your 0, it gives you 0 over 0. Well, that means it's reducible, but we're going to have to find out how to reduce it. So for that, I wanted to show you this first line here comes from this, the square root of x plus 1 minus 1. We take it times sort of its pair. And this is the square root of x plus 1 plus 1. The only difference here, minus 1 and plus 1. Now, that's not the problem. That's kind of a side issue. So now we're going to plug that into the problem. Now you'll notice here's the original denominator. Here's mine. The one above it, that's mine. So when you collect your terms and multiply this out, you come up with over x, and your x's cancel. See, that's usually what 0 over 0 indicates, is you're going to reduce the fraction, possibly completely reduce it and put it away. So now I come back and I plug in the 0 and I get 2. So this is the way to reduce by radicals in kind of a combination. It isn't conjugate pairs, but it's like it. And then I want to emphasize again the left and right hand behavior. When this little negative sign is in the exponent on this letter, the number here, or it's positive on it, that means from the right side, and this means from the left side. This one here is an absolute value problem, which if you plug it in, you get 0 over 0. If you plug your 0 in, you get 0 over 0, which is indeterminate. And indeterminate means to keep factoring, keep trying. So we split our absolute value into two parts. We split it into the negative x over x and the positive x over x, which gives us negative 1. Y equals negative 1 is one side of the graph, and y equals positive 1 is the other side of the graph. So let's look at this according to the negative left side of 0. Our line right here, x equals 0, comes down. Only thing existing to the left of that is the y equals negative 1 graph. So that is the left-hand behavior for the limit. Now limit is y, limit is output. So this is the level, the y level that we will end up at as we approach 0. Turn it around, what if we approach it from the right-hand side of 0? In that case, it's x over x, which is 1. So from the right-hand side, the limit is 1. If I approach it from both sides of 0, that would be the original problem up here from both sides of 0. The limit does not exist, D and E. Let's take this idea, does not exist limits. There are several cases. The first is unbounded. In fact, several are going to be unbounded. And unbounded is usually when I have functions with x in the numerator and x in the denominator. These are hyperbolas, they're hyperbolic, like the one to the right, which is the graph of 1 over x. As we approach 0, oh, by the way, we have a vertical asymptote and a horizontal asymptote in hyperbolas of this type at y equals 0 and x equals 0. So as I take the path of the function, which is right here, going this direction, down this direction, and over here is coming in towards 0, x is 0, and then towards 0 it goes up. This from 0 from the left side is down here, negative infinity. Now we're approaching x equals 0 this way, and then staying on the path, you go down forever, that's negative infinity, and then on the right side of 0, you go up as you go towards 0 forever to positive infinity. From both sides, we would say they're different limits. Negative infinity is different than positive infinity. Then we would say it does not exist. Here's another graph. It's basically the same thing, except we emphasize here the number 2. If you plug 2 in here, you get a 0 in the denominator, which means undefined, which means the vertical asymptote is at x equals 2. You can see that in the drawing. There it is, x equals 2. And the horizontal asymptote is still y equals 0. So again, let's take this and as we approach, in this case, 2, positive 2, from the left side, we follow this path right here. As we approach it, we're forced by the path to go down to negative infinity on the left side. On the right side of 2, we're forced to go up to positive infinity. From both sides, that's the original problem, the limit does not exist because the two limits are not going the same direction. Let's see this again with the 2 minus x squared. Notice now the vertical asymptote is still x equals 2 and the horizontal is y equals 0. Because of the squared in the denominator, the graph looks a little different. It looks like going up and going up. So let's run through this again. As we get close to 2, we end up going to positive infinity on the left side with the negative there, and the right side to positive infinity, and together the limit, which is the original problem, is to positive infinity. They're both going to positive infinity. So they agree on that. So here's some rules for unbounded. The first is what we just did. The left and the right limits do not agree, so it's a does not exist. I call that DUI because of the test of whether or not you've been driving under the influence. You have to put your finger on your nose and your left hand finger on your nose, and if one hits your forehead and one hits your chin, you're going to have a DUI. So those are DNEs. Number 2 here we just did several examples of unbounded from the left and the right, typically a vertical asymptote. And the last one we didn't do, and you can do that on your own, it's called an oscillation. And this is an example of that. Put your graphing calculator into radians and do the sine of 1 over x. That'll be an example of an oscillation. And also, without spending a great deal of time, I want to state the limit rules, the limit operations, when f of x has a limit of L and g of x has the limit of M. We can follow the add and subtract rule here, the multiply rule, the divide rule, and the power rule. So I won't go into those, but those are the rules of operations that they operate limits by. Part 3 is to follow. Part 1 preceded. Check them out. In the upper right-hand corner, make sure you subscribe. In the upper left-hand corner, make sure you check out other videos. Likes are below and make comments on topics you need.